Welcome to The Explainer, where we turn complex problems into clear stories. Today, we're putting on our detective hats to solve a really fascinating chemical mystery. So let's get right into it.
Okay, so here's our case files straight from the lab. A student takes the exact same amount of a pretty strong acid, hydrochloric acid, and adds it to 3 different solutions. You've got pure distilled water, something called buffer A, and another one called buffer B. And as you can see from the evidence right here, the results are, well, they're wildly different.
And this leads us to the big mystery we need to solve. How can the same exact action lead to such different outcomes? I mean, look at the water. Its pH just completely collapsed. But the other two? They barely moved. They really held their ground. And what is that subtle clue that makes buffer A different from buffer B? This is the puzzle we're going to solve together, step by step.
To crack this case, we have to understand the key player here. And that means we need to put a spotlight on our prime suspect, the buffer solution itself. What exactly is it, and what does it do?
So a buffer is a really special kind of solution. Its whole job is to keep the pH stable. When you try to make things more acidic or more basic, the buffer just pushes back. It's like a chemical shock absorber, smoothing out what would otherwise be a crazy, bumpy ride for the pH.
So what's the buffer's secret formula? You might think it's some super complicated thing, but it's not. It's actually this really elegant partnership between 2 related chemicals. A weak acid, think of something like the acetic acid that's in vinegar, and what's called its conjugate base. That's basically the acid after it's lost a proton. These two are a team.
And here's how that team works. This is the key. When that flood of strong acid, which is really just a ton of H+ ions, pours into the solution, that conjugate base part of the team just springs into action. It's like a chemical sponge, soaking up all those aggressive H+ ions and turning them right back into the harmless weak acid. So the threat gets neutralized before it can cause any real damage to the pH.
Okay, now that we know the buffer's secret weapon, let's go back to the evidence in our case file. It's time to compare the crime scene in that beaker of water with what happened in buffer A. Let's see that secret formula in action.
And wow, this just perfectly shows you the power of a buffer. Over on the left, you see the water. It had absolutely no defense system. Its pH went from a neutral 7 all the way down to a superacidic 1.3. That is a catastrophic change. But then look to the right. Buffer A, armed with its acid-base team, it barely even flinched. The pH only moved from 4.5 to 3.9. It totally held the line.
So that's the bottom line here. Water is just vulnerable. It has nothing in it to fight off that incoming acid. The buffer, though, it came ready for a fight. That weak acid and conjugate base pair is the entire reason the outcomes were so different. It's really the hero of our story.
But wait a minute, our mystery isn't totally solved yet. We figured out why the buffers worked, but we haven't figured out why one of them worked better than the other. So now we've got to investigate that subtle clue that separates buffer A from buffer B.
This is the final twist in our case, right? If you look back at the evidence, both buffers started at the exact same pH, 4.5. But after that acid was added, buffer A dropped to 3.9, while buffer B only went down to 4.2. Buffer B was clearly stronger, more resilient. So what does that tell us?
Okay, so this clue reveals something new and really important. You see, the starting pH of a buffer depends on the ratio of its weak acid to its conjugate base. Since A and B started at the same pH, they had to have the same ratio. But because they performed differently, that tells us they must have had different total amounts of those ingredients. Buffer B was just more packed, more concentrated.
And there's a name for this property. It's called buffer capacity. It's basically a measure of how much of a punch a buffer can take before it starts to get overwhelmed. A buffer with higher concentrations, like our buffer B, has a bigger army of those acid-soaking sponges. It just has more stamina to fight off pH changes.
And looking at the data this way just makes the whole story crystal clear. I mean, look at the bar for water. It's enormous. A pH change of 5.7 units. The change for buffer A was tiny in comparison, just 0.6. And then buffer B, with its higher capacity, even more impressive. A change of only 0.3 units. The visual evidence here is just undeniable.
All right, let's put all the clues together. We can close the file on this case and just summarize what our investigation has really taught us about the incredible power of buffers.
So, here are the key takeaways from our investigation. First, buffers are like chemical bodyguards for pH, and they use that weak acid/base team to do it.
Second, it's the base part of that team that's the real MVP, neutralizing incoming acids. And finally, the buffer's overall strength, its capacity, all comes down to the total concentration of that team. More concentration means way more protection. Case closed.
And here's why all of this matters so much, beyond a chemistry lab. This isn't just some clever textbook problem. This exact principle is happening inside your body right this second. Your blood is a buffered solution, and it works tirelessly to keep your pH at about 7.4. If it swung around as much as the water in our experiment did, you wouldn't survive. Buffers are literally essential for life.
So we've solved this one case, but by doing that, we've really uncovered a fundamental secret of nature. And it opens up a whole new world of questions, doesn't it? Now that you know how these chemical shock absorbers work, where else can you spot them? In the foods you eat? The medicines you might take? What about in the oceans and the soil all around us? These invisible guardians are at play absolutely everywhere.